That's his law. You have this diagram right here where there's one entry point for flow and there's an exit point for that flow. In the middle, there is a wind turbine, right? And the surface area of that wind turbine would just be S. And so through this area right here, there goes a velocity, right? So to the left of it, where air is entering, there's the cross-sectional area and a velocity going in, and then going outwards, there's another area, cross-sectional area, and another velocity value going out. And so the mass flow rate on all these points are actually going to be equal to each other. And so you have the density of air, which is given by rho, times this by A1 V1, which is the mass flow rate of this area. The mass flow rate of the middle area with the wind turbine is going to be PSV. This is going to be equal to air density times this by cross-sectional area of A2 times this by the velocity going outwards. So by using the momentum balance equation from the previous homework parts, we can apply the same concept. So the force being applied in this case would just be the force of the turbines in the system. And then you have the momentum going inwards. In this case, it would be the mass flow rate times this by velocity going in. But in this case, we can actually call V in as V1, since V1 in this case is the velocity going inwards. So we're going to replace the terminology. V in is now going to be V1. The mass flow rate is also equal to rho times this by cross-sectional area of the entry point times by V1 as well. And so we can write this as rho A1 V1 squared. We can apply the same idea to the momentum going outwards. That will be the rho, or air density, times this by the exits cross-sectional area, minus, or times this by V2 squared. We can actually simplify this a little more though. So we can see that the mass flow rate is also equal to rho. Oh my god, the thing is on the fucking screen. Well, we can also recognize this equation as 0 is equal to F plus. Now, with this, we know that we did the mass flow rate times this by V inner minus mass flow rate times V out, right? Well, we can actually set that mass flow rate equal to this. That will give a constant coefficient for each of these two parts. So we can actually just write PSV times this by V1 minus V2, and this is still equivalent to this expression right here. We can actually get rid of this negative sign right here by recognizing that power is equal to the force times this by the velocity, right? And so with this, you now get power is equal to rho times this by SV, quantity V1 minus V2, times this by V. Oh my god. And so we need to remember that there is negligible friction, right? So we can actually write an expression showing that off. That expression will be rho SV times this by V1 squared over 2 minus V2 squared over 2. And so this is assuming that there's no friction and that all the kinetic energy from the air in and air out are converted into power. We can actually set these equations equal to each other. So we got rho SV times by V1 minus V2 by V is equal to rho SV over 2, since we can pull out the 2, or the 1/2, sorry. And so this right here is just equal to V1 minus V2 squared. And so we can actually write this as V1 minus V2 multiplied by the quantity of V1 plus V2, right? And so with a bit of canceling, we're left with the velocity of the turbine is actually just going to be equal to V1 plus V2, all this over 2. So now we can plug in variable for the velocity for the turbine into this equation right here. So now we have P is equal to the power, assuming no frictional forces, is equal to 1/2 rho S times by V1 plus V2 times this by V1 squared over 2 minus V2 squared over 2, which then you can also take out that 1/2. Now you're left with 1/4 rho S V1 plus V2, and then V1 squared minus V2 squared. So we can actually start expanding this a bit. Let's see. P is equal to 1/4 rho S. We have V1 cubed minus V1 V2 squared, and then plus V1 squared of V2 wait, no, wrong one. And then plus V two. Wait, I got it wrong. Oh, geez, sorry. So it's V1 cubed minus V1 V2 squared plus V1 squared V2 minus V2 cubed. We can actually take out a V3 from the parentheses right here. Oops. When we do that, or V1 cubed, sorry, we get 1 minus V2 squared over V1 squared plus V2 over V1 minus V2 cubed over V1 cubed. Now to simplify this a little more, we can actually set a variable for V2 over V1. We're going to just call it R. So R will equal V2 over V1. With that, we can simplify this a little more. 1/4 rho S V1 cubed is by 1 minus R squared plus R minus R cubed. And so we need to recognize that the R is the ratio of the velocity of the air leaving relative to the velocity of the air entering the system. So what we can do next is take the derivative of the power in respect to R, You see the constants stay the same, and then inside the parentheses are left with negative 3r squared minus 2r plus 1. And here we just need to complete the square. So when we complete the square, we're left with 1 plus r, and then 1 minus 3r. And so r can equal either negative 1, or it can equal 1/3. Now we choose 1/3 because r can't be negative in this case, so the optimal ratio is 1/3. And again, that ratio will be v2 over v1. So every 1 part air, or for every 1 part velocity of the air leaving, there needs to be triple amount of that velocity entering in order for that ratio to be optimal. So now we can figure out what the optimal power ratio is. So this, we'd use this equation right here, 1/4 rho s v1 cubed, 1, and then we just plug in 1/3 for each r, so r squared, that's negative 1/9, plus, let's do that, plus 1/3 minus 1/27. Doing this, we can set everything equal to above 27, so we get 27, 27 over 9 is negative 3, 27 over plus 3, 27 over 3 plus 9 minus 1. This we get 24, 24 plus 9, 33, right? 24, then 33 minus 1, 32 over 27. So now you're left with 1/4 times this by ratio 32 over 27. So then you get the ratio 32, then 4 times 27, 8, 1/8. So now you're left with this ratio and this expression for P optimal. Well, we can actually express this in a different way, and this is typically how it's expressed. We can express it using terms of kinetic energy. So with that, this right here, this actually equates to 8 over 27. 27 is still over here, but now it's going to be 16 over 27. And this right here is the ratio for P optimal. This is the optimal ratio of the outlet air velocity to the inlet air velocity right here.